In the last lecture, we have discussed the propagation of plane electromagnetic wave in free space. Today, we are going to discuss its propagation in an isotropic dielectric medium. You know what does isotropic dielectric medium means? Actually, an isotropic dielectric medium is a non-conducting medium whose properties are same in all directions. In other words, you can say that the properties of this medium is independent of direction. Actually, this is due to the scalar nature of the dielectric constant or permittivity of this medium. You know, in case of isotropic dielectric medium, the electric displacement vector D and the electric field vector E is related by this linear relationship. D is equal to epsilon into E, and here epsilon is actually permittivity of the dielectric, and it is given as epsilon naught into epsilon r into E. In fact, this epsilon r is actually a scalar, and you can say this is a positive scalar. Epsilon r is a positive scalar. Epsilon r, this is a positive scalar, and its value is independent of the medium, or you can say direction. So in this condition, if we find that x, y and z components of the electric displacement, this will be simply dx equal to epsilon naught epsilon r ex, where ex is x component of electric field vector E, and similarly dy equal to epsilon naught epsilon r ey, dz equal to epsilon naught epsilon r ez. But in case of an isotropic dielectric, you will see that this epsilon r is not a scalar quantity, but it will be a tensor. In fact, that is the problem which I will discuss in the next lecture. Today we are going to discuss the propagation of electromagnetic wave in isotropic dielectric, where these linear relationship between D and E will exist. As you have seen, whenever we discuss the wave propagation in a particular medium, we first of all find the wave equation, and that wave equation is found actually by solving Maxwell's field equations in that particular medium. So again, let us start with the general form of the Maxwell's equation, and after that we will actually find Maxwell's equations particularly in this particular medium, and then after some mathematical calculation we will find the wave equation. You know, Maxwell's field equations are divergence D, which is equivalent to del dot D equal to rho, divergence B, which is equivalent to del dot B is equal to 0, and curl E, that is del cross E, is equal to minus del B by del T, and curl H is equivalent to del cross H, and this is equal to J plus del D by del T. You know the meaning of each and every term in this equation, and also you know that in this equation this J is equal to what? This J is equal to sigma E, where sigma is actually electrical conductivity. You know that this equation J equal to sigma is sigma into E is actually the vector form or the microscopic form of Ohm's law, and B is equal to mu h and D is equal to epsilon E. Here mu is permeability of the medium. But in case of isotropic dielectric, since isotropic dielectric is a non-conducting material or medium, so its conductivity is 0, and in this case this free charge density is also 0, rho is equal to 0. And so if sigma is 0, from this form of Ohm's law, J equal to sigma E, you can see when sigma will be 0, J will be also 0. So if we will actually impose these values of sigma, not sigma but J and rho in equation 1, then we will get the Maxwell's field equations, particularly in isotropic dielectric medium. So after these substitutions, what are the Maxwell's field equations in isotropic dielectric medium? You can see we will replace this d by epsilon E, and in RHS there is rho and which is 0. So this will be simply epsilon into divergence E equal to 0, as epsilon is a non-zero constant. So that will be simply divergence E equal to 0. And again B will be replaced by mu H and D will be replaced by epsilon E. So you can see after this substitution, the Maxwell's field equations becomes like this, which I have mentioned here, and say this is actually equation 2. So Maxwell's field equations in isotropic dielectric is given as divergence E equal to 0, divergence H equal to 0, curl E equal to minus mu del H by del T, and curl H equal to epsilon del E by del T. Now we will find the wave equation, and I hint you have to follow the same step for finding the wave equation as you have followed in case of free space. So what we actually do here, we will take the curl of a curl equation. You are seeing here that Maxwell's equations defined in equation 2C and 2D are curl equation, and to find the wave equation we will take the curl of these equations. So let us take curl of equation 2C. When you say we are taking curl of equation, it means we will operate the operator del cross on that equation. So this will be simply del cross E, and this is minus del cross mu into del H by del T. And from the definition of triple vector product, you can simplify this LHS of this equation, and what will be this? This will be actually equal to del dot E minus del dot del E, and this is equal to as you know, the operator del cross and del T are interchangeable. Their interchange is permitted. So let us interchange these two operators. As mu is a constant, so we can take it out from the operator. So this will be simply minus mu del T del cross H. Here simply the operators del cross and del T has been interchanged. Now let us make the use of equation 2A and equation 2D in this equation. You can see from equation 2a, what is this divergence of E? This is actually 0, and del cross H is defined in equation 2d. So making use of equation 2a and 2d, we get what we will get after making the use of these two. You can see from here, the first term in LHS will be 0, and this will be del square E, and del cross H will be replaced by epsilon into del E by del T. And so we will simplify this result by using these two equations. So our result will be actually equal to minus del square E equal to minus del square E equal to minus mu into epsilon del 2E by del T square. You can omit the negative sign in both sides, so the final result will be del square E equal to mu into epsilon del 2E by del T square. Let us say this is equation A. Now, in similar manner, if we will take the curl of the equation 2D, see here, this is equation in fact 2D, and we will take the curl of this equation 2D. You are seeing here only H is here instead of E, and epsilon is instead of mu, and E is instead of H. So, and after that we will make the use of equation 2b and 2c. We will get the similar result for the magnetic intensity vector H. So similarly, I am just writing it in similar manner. Similarly, taking the curl of equation 2D, we get, actually what we will get, this will be del square H equal to mu into epsilon del 2H by del T square. You can simplify this result by the same manner as I have discussed just now in the above part, and so I have just written it directly without solving the Maxwell equation. And now you can see the form of equation A and equation B. In fact, it is easy to observe that these two equations are simply in the form of the classical wave equation. You know what is classical wave equation or D'Alembert equation. So you can write now the classical wave equation. Classical wave equation is given as how we write the classical wave equation? You know, it is written as D'Alembert's this is Laplacian psi, that is del square psi, this is Laplacian operator, and this is equal to 1 over v square del 2 psi by del t square. You know it. We have definitely, you have studied it in waves and oscillation. And in this equation, you know this v is what? This is phase velocity of the wave. This is phase velocity of the wave. It is also called wave velocity, or the popular term is phase velocity. So you can see, if we compare these equations A or B with the equation C, we find that these equations A and B are simply the classical wave equation, and in equation A the wave function is electric field vector E, and in equation B the wave function psi means the magnetic intensity H. So we can say that these two equations actually refer a particular type of wave propagating in space. Since here the wave functions are actually either the electric field vector E or magnetic field vector B, so in fact these two equations will represent a particular type of wave whose wave functions are electric and magnetic field vector. And you know, if the wave functions are electric and magnetic field vectors, such a wave is called electromagnetic wave. So you can say that comparing equations A or B with C, we find that E is equivalent to psi and H is equivalent to psi, and in fact you know this psi is wave function. So you can say E and H are propagated as waves, and such a wave is called electromagnetic wave. Electromagnetic wave. Now we can find the wave speed or phase speed of this electromagnetic wave by comparing equation A or B with equation C. You can see from these two equations, in place of 1 over v square in equation A and B, there is mu into epsilon. So definitely this mu into epsilon will represent 1 over v square. So from here we can find the phase velocity of the electromagnetic wave traveling in this isotropic dielectric medium. So comparing A or B with C. The phase velocity V of electromagnetic wave is given as, you can write mu epsilon is equal to 1 over V square, and so from here we can find the phase velocity V in isotropic dielectric medium as 1 over root over mu into epsilon, and say this is equation 3. So this is the expression for phase velocity of electromagnetic wave in an isotropic dielectric medium. Now we know in case of isotropic dielectric medium, this permittivity epsilon is equal to epsilon naught into epsilon r, where epsilon r is called dielectric constant or the relative permittivity of the medium. And at the same time, you know this mu is equal to mu naught into mu r. Here mu r is relative permeability and mu naught is permeability of free space. And therefore, the expression for V can be written as 1 over root over mu r into epsilon r mu naught into epsilon naught. But we know that this 1 over root over mu naught epsilon naught, you have studied in previous lecture that this is equal to C, and this C is actually what? This is a speed of EMW in free space. So this result, after the use of this equation C equal to 1 over root over epsilon naught into mu naught, this V can be written as C over root over mu r into epsilon r, mu r into epsilon r. And we know that this mu r and epsilon r is greater than 1 for any isotropic dielectric medium. So in this condition, you can say the denominator is a number greater than 1. So definitely this V will be smaller than C. So you can say as root over mu r into epsilon r is greater than 1. So this V will be less than C. It means in an isotropic dielectric medium, the electromagnetic wave travels at a speed V, which is smaller than its speed in free space. This, in fact, the speed of electromagnetic wave in free space is highest. In any other medium, its speed will be smaller than the speed in free space. Again, we can define an important property, that is, which is actually refractive index or index of refraction in this condition. You know that refractive index N is defined as how we define it? You know, this is defined as C over V. C over V. This is just the definition of the refractive index of a medium. And so, if we will substitute the value of this V from equation 4 in equation 5, what will be our result? So, using 4 in 5, you can see this C will be actually cancel out, and the result will be N equal to 1 over root over mu r into epsilon r. That is, N will be simply a square root of mu r into epsilon r. So after this, after the use of equation 4 in 5, we will get N equal to root over mu r into epsilon r. Actually, this is also an important result, but you can say very important result. Actually, for a non-conducting medium, you know, the isotropic dielectric medium is a non-conducting medium, and at the same time it is also non-magnetic. You cannot induce magnetism in it. So we say that the isotropic dielectric medium is a non-magnetic medium, and for a non-magnetic medium the relative permeability mu r is equal to 1. So for a non-magnetic, when you say non-magnetic, it means magnetism cannot be developed in it. So for a non-magnetic medium or material, you can say this relative permeability mu r is equal to 1. And if mu r is equal to 1, you can see from above, then the refractive index N will be simply equal to a square root of epsilon r, and you can say that N square will be equal to epsilon r. This is also a very important result, invariably used in different conditions, and say this is equation 7. So from this result we have just calculated the value of the index of refraction of the medium, and you are seeing here that the square of index of refraction is simply equal to the dielectric constant of this medium. Actually, this equation 7 is called Maxwell's relation, and this has been accurately confirmed by experiments for long waves, that is radio frequency and slow infrared oscillations. So equation 7 is known as Maxwell's relation. Maxwell's relation, and it has been verified, experimentally verified, for long waves. When you say long waves, it means waves of longer wavelength, like radio waves or infrared waves. For such wave, this relation has been verified. Actually, in visible region of the electromagnetic spectrum, the relation is also fairly well satisfied by some substances such as hydrogen, carbon dioxide, nitrogen, oxygen. So in visible region this is also true. In visible region of the spectrum, equation 7 is valid for H2, CO2, N2 and O2. For such material, this relation actually holds. But for many other substances, it fails. For these materials, this relation holds, but there are several substances for which this relation does not hold. Actually, when as a rule the substance shows infrared selective absorption with water, the failure is especially marked. In fact, for water you can see that mu r is almost equal to 1 and epsilon r is 8, and so that n should be equal to what? So n should be equal to epsilon r is not 8 but 81, and so you can say for water, let us take for water mu r is almost equal to 1 and epsilon r is almost equal to 81. The dielectric constant of water is 81, and therefore what will be this n? N will be almost equal to root over 1 into 81, and this should be almost equal to 9. But it is well known that the index of refraction for light, which is almost equal to 4 by 3. So you know, but n equal to 1.33 for water. So you can see this result does not hold for the material like water. So you can say this is not a universal relation, although it holds fair for some of the substances, but it does not hold for all the dielectric materials. So it fails in case of water. If this result will hold for water, then the refractive index of water should be equal to 9, but we know that refractive index of water is very close to 1.33, so you can say this result does not hold for water. Actually, here it is also to note that as epsilon r is greater than 1, so velocity of light in isotropic dielectric medium is always less than c, and in this condition we can say that as we have already seen, V is less than c. V is less than c. So the velocity of electromagnetic wave in isotropic dielectric medium is smaller than c. So it is possible for high energy particle to possess velocity to exceed v, although any material particle cannot have a velocity greater than c. But since velocity of electromagnetic radiation in a dielectric medium is smaller than c, so velocity of a material particle traveling or moving in that medium may be greater than this v. And when the velocity of the material particle is greater than v, what will happen? Actually, when such particles pass through a dielectric medium, in that condition, a bluish light known as Cherenkov radiation is emitted. Actually, we will discuss this Cherenkov radiation in classical electrodynamics sometime later in detail. But this is the basic principle of Cherenkov radiation, that in a dielectric medium, a material particle travels at a speed greater than the speed of electromagnetic wave in that medium, that is compared with velocity v. And in that condition, a bluish light actually is emitted by the particle, and such a light is known as Cherenkov radiation after the name of a Russian scientist Cherenkov. And due to this interaction, the uniformly moving charged particle with velocity v actually emits the Cherenkov radiation. So as v is smaller than c, so velocity of a charged particle in a medium may be greater than v. If, not if, but you say in this condition, the particles emit a radiation known as Cherenkov radiation. So you can say in short that in free space no material particle can travel at a speed greater than the speed of electromagnetic wave in free space, that is c. But as in a medium the speed of electromagnetic wave v is smaller than c, so it is possible that a charged particle moving in that medium may have a velocity greater than c. And when the velocity of the charged particle moving in a medium is greater than v, v means velocity of the electromagnetic wave particularly in that medium, then actually a bluish light is emitted by the charged particle, and that is known as Cherenkov radiation, in fact after the name of its inventor, which was actually a Russian scientist. So this was all about the refractive index of the medium. Now let us further see the wave equation which we have obtained here in equation, you can say in equation B, A and B. And now let us write the plane wave solution of the wave equation in A and B. So now the plane wave solution of equation A and B are given as, we will write E equal to, This is solution of equation A, and we will write it as E equal to E naught e to the power I k dot r minus omega t, and h equal to h naught e to the power I k dot r minus omega t. These are actually the plane wave solution of the wave equation defined in A and B. Now we have discussed already in the previous lecture, due to this form of the solution of the wave equation, we have two operators, and these two operators are del is actually equivalent to ik. You know here this k is actually the wave vector, and we have also obtained that the operator del t is equivalent to minus I omega. And so now we can replace these operators del and del t in Maxwell's equations, and after the use of these two equations, Maxwell's equation will be in a convenient form, and you have seen in previous lecture, from that convenient form it is easier to discuss the different properties of the electromagnetic wave traveling in that particular medium. So using these Maxwell's equations become, for your convenience I am writing here in left side the original Maxwell equation, and after the use of these two operators, what will be the Maxwell's equation in right side. You know the first Maxwell equation in isotropic dielectric medium was what? That was del dot E equal to 0. And when we will write this equation del dot E in terms of this, you can see here this will be ik dot E equal to 0, and this implies k dot E equal to 0, and let us say this is A, and the next equation is what? This is del dot H equal to 0, and so you can see this will be ik dot H equal to 0, and from here we can write this k dot H equal to 0. Say this is equation B. The third equation is del cross E is equal to minus mu del H by del T, and so you can see from here that this will be ik cross E, and this is equal to, since del T is minus I omega and minus is already present here, so minus will be cancelled out, and this will be mu omega H, and I will remain here. And so after the cancellation of this I, the equation will be K cross E is equal to mu omega H, and say this is equation C. K cross E equal to mu omega H. Now the fourth equation is what? Fourth equation is del cross H. Del cross H equal to epsilon del E by del T, and we can write it in this way. This will be IK cross H, and this is equal to, here del T will be replaced by minus I omega, so this will be minus I epsilon into omega E. Again I will cancel out, and so our result will be K cross H equal to minus K cross H equal to minus epsilon omega E. Epsilon omega E. And you can write this minus sign in left side to maintain the symmetry. So I am just writing this minus sign in left hand side. So you can write minus K cross H equal to epsilon omega E, and say this is D, and what will be the equation number? Actually this will be equation 8. Say this is equation 8. So we have transformed the Maxwell's field equations in an isotropic dielectric medium by the use of these two operators, del equal to IK and del T equal to minus I omega, in a convenient form, as we have done in case of wave propagation of electromagnetic wave in free space. And now in next lecture we will see that the discussion of different properties of electromagnetic wave traveling in isotropic dielectric medium will be very convenient, very easier by the use of this form of Maxwell's equation. So now we will discuss these properties of electromagnetic wave in traveling in isotropic dielectric medium in next lecture.